Transition elements. Transition elements. Okay, so the definition of a transition element. A transition element is a D block element. Transition element is a D block element that forms at least one ion. That forms at least one ion with an incomplete D subshell. Okay, so that's the definition of a transition metal ion. So when you think of the D block elements, I'll just show you the periodic table. When you think of the D block elements, this is the D block, this middle section, scandium to zinc, but scandium and zinc are not transition elements. Titanium, vanadium, the bits in the middle are, okay? So scandium and zinc are D block elements, but are not transition elements because they do not have an incomplete, at least one ion with an incomplete D subshell. Okay, so remember with the electron structure, the ones you've got to be careful of are chromium for the electron structure. Chromium is argon, and then 3d5 4s1, which is an exception. Remember, it should really be 3d4 4s2, but because it's more stable to have a partially filled subshell, a half-filled subshell, one electron in each orbital, an electron comes back, and so it is actually 3d5 4s1. And the other exception in terms of electron structure is copper. Copper is 3d10 4s1, and again it should really be 3d9 4s2, but because it's more stable to have a completely filled 5 orbitals D subshell, then an electron comes back, so it's not that, it's 3d10 4s1. Okay, another thing to remember with electron structure, if we take, for example, let's take iron for example, right? So iron is everything up to argon, and then iron is 4s2, 3d 1 2 3 4 5 6, 3d6. So when you form an ion of iron, so if we form the Fe2 plus ion, we are losing two electrons, so you lose the 4s, so the ion is 3d6, the ion of iron. Okay, you lose the 4s electrons. Okay, very quickly, the physical properties of transition elements. The physical properties. So like other metals, they're good conductors of electricity, just like other metals, good conductors of electricity. They have high melting points, just like other metals, high melting points, high densities, and they're useful in construction materials like iron, high densities. Those are the physical properties of transition elements. Okay, now the chemical properties of transition elements. Remember, scandium and zinc are not transition elements. Okay, the chemical properties of transition elements. The chemical properties of transition elements are that they form coloured compounds form coloured compounds. Okay, two very common ones that you should know about is, you should know about, for example, potassium dichromate, which is used in the oxidation of alcohols, and that's an orange compound. And chromium is in the oxidation state +6, because oxygen is -7, sorry, it's -2, and the 7 of them is -14, +2, so chromium is +6. Another common one is potassium manganate. And potassium manganate is a purple colour, and manganese is in the +7 oxidation state. So transition elements form coloured compounds. Another chemical property is that they have, which is shown here, transition elements have several different oxidation states. Several different oxidation states. Okay, and that's a good example here, that we have +6, +7, but chromium in the oxidation of an alcohol, chromium 6+ becomes chromium 3+, and that is a green colour. Okay, so they have various oxidation states. Manganese also can exist in the manganese 2+, which is a very light pink colour. Okay, so several different oxidation states, which means that they're very useful as catalysts. Okay, they are good catalysts because they've got several different oxidation states. Good catalysts as well. Okay, and the final property is that they form complex ions. They form complex ions. Okay, form complex ions. So what is a complex ion? Well, we'll talk about that more in a second. First, how do you test? How do you test for transition element for the ions? Okay, how do you test for the ions? So you add sodium hydroxide, and the ones you need to know are copper. If you've got copper 2+ ions, that's a blue solution, and you add hydroxide, sodium hydroxide, which is also solution, and then you form a precipitate, solid precipitate of copper 2 hydroxide, and that's a blue. It looks like jelly, so we call it a gelatinous precipitate. Be careful with your spelling. Precipitate. Okay, and this test for transition element ions, transition metal ions, they're called precipitation reactions. Sorry, my handwriting is not very good. Precipitation reactions. Precipitation reactions. Okay, the other colours you need to know are, if you take cobalt, okay, cobalt 2+, which is pink, and you do exactly the same again. You add sodium hydroxide, okay, then you get cobalt hydroxide. Now be careful when you're writing cobalt. Cobalt is not carbon monoxide, okay? It's a small o, so be careful when you're writing it. And this is a blue, I'm just going to put PPT for precipitate, a blue precipitate, which turns a beige colour upon standing. Okay, turns beige, which is like a light brown, upon standing. Okay, the other two colours you need to know is, you need to know iron 2+ is a pale green solution, light green, and just the same with hydroxide, just the same, it forms iron hydroxide solid, which is a green precipitate. Yeah, and then finally the last one, the colours you need to learn for A-level chemistry, you need to know iron 3+, which is a yellow solution, But be careful now, that's going to be 3 hydroxides. You have to put the state symbols, that's AQ. You have to put the state symbols, and that'll be Fe, OH3 solid, and that forms a rusty brown, like an orange brown, rusty brown precipitate. Okay, so that's called precipitation reactions. That's the test for transition metal ions. Okay, let's get on to so the chemical properties of transition elements. They've got form colored compounds. You recognize some of those already. They have several different oxidation states to the transition element ions. They're good catalysts, and they form complex ions. So let's talk about forming complex ions. So this is when the transition element, the ion, the transition metal ion, is in solution. Okay, so complex ions. So in solution, the ions of transition metals, form complex ions. All right, so for example, we say copper 2+. We just simplify. Blue solution, we say copper 2+, but that's not actually the case, right? Copper 2+ is surrounded with 6 water molecules. Now, water molecules are neutral, so it doesn't change the overall charge. You put square brackets, and that is called a complex ion. So that's like a short version, and that's the proper full version. It's called a complex ion. So it's a transition metal ion that is bonded to, these are called ligands. Okay, so let's give an example then. Let's give an example of this. So if we take, right, these are called ligands. So if we take copper, right, copper, and it is bonded to 6 water molecules. Remember from AS chemistry, 6 water molecules, the 6 bonds is a octahedral. The straight line is in the plane of the paper, the dash is going back, and the wedge is sticking out. So it's an octahedral shape. You remember a bond angle 90 degrees. Okay, so the water molecules are bonded to the copper, and what happens is the water molecules has got a lone pair of electrons. Well, actually 2 lones, a pair of electrons. Okay, and the lone pair of electrons is donated to the transition metal ion. Okay, so it's the oxygen from the water that is bonded to the transition metal ion. It's the oxygen from the water, because the lone pair of electrons is donated to the transition metal ion, and then you've got the water, you know, the H2 just gets filled in around like that, an octahedral shape, and then you put your square brackets round, which donates a complex ion, and the charge 2+, and that is a complex ion. Okay, so we need some definitions. Okay, water, this water molecule is called a ligand, and the definition of a ligand is a molecule or ion, which donates a lone pair of electrons, which donates a lone pair of electrons to the central metal ion. And this is something that transition elements do to form a coordinate bond. Okay, so that is called, that bond there, that bond there is called a coordinate bond. Okay, there's another term for that bond in organic chemistry. When a bond is formed and the electron pairs come from the same atom, it's called a dative covalent bond. So you can also call it a dative covalent bond as well. Okay, so it forms a coordinate bond or a dative covalent bond. Right, and that's a complex ion. So when we represent Cu2 plus in water, in solution, it's not really like that. It's actually surrounded with 6 water molecules. The water molecules called ligands. The whole thing is called a complex ion and forms a coordinate bond. Right, the coordination number is just the number of coordinate bonds. The number of coordinate bonds. So the coordination number here is 6 because there are 6 coordinate bonds. Okay, other common ligands. So we've got ligands. So you have water, which is a very common ligand because it's got lone pair of electrons. Okay, other common ligands are ammonia. Ammonia can be a ligand because it's got a pair of electrons. You could have something like chloride. You could have hydroxide. You can have less well-known ones, but you might come across them as cyanide. And this one here, you might come across this one, which is the thiocyanate ligand. Okay, just gonna write the name underneath. Thiocyanate ligand. Okay, they've all got a lone pair of electrons which can be donated to the transition metal ion. They are all called monodentate ligands. Monodentate. That's because they bite, dentate, they bite, bond once to the transition metal ion. Okay, so lots of terms, there's lots of terms. So you come across before in organic chemistry. In organic chemistry, you've come across stereoisomerism. Stereoisomers, okay? It's just the same in inorganic chemistry as well. Stereoisomers are molecules. Stereoisomers are molecules or complex ions. Molecules or complex ions with the same. Sorry, my writing's not very good. I think it's the pen. With the same structural formula. The same structural formula, but with a different spatial arrangement. With a different spatial arrangement of the atoms in space. Okay, so stereoisomers, same structural formula, different spatial arrangement of atoms in space. So if you have a complex ion, like this complex ion, for example, let's take cobalt, right, with 4 water molecules, 4 water ligands, and 2 chloride ligands. Okay, that's called a chloride because it's Cl minus. Chloride ligand. Cl minus. Okay, Cl minus, right? So if you have it, it's octahedral because there are 6 ligands, so it's octahedral. So you have your octahedral shape, dash going back into the paper, wedge sticking out. Okay, 3D. So if you have your chloride here and your chloride there, okay, and then if you have your water, the oxygen is the bit that's bonded. If you have your water there, okay, Okay, now and put the overall charge. Whoops. Okay, you do not write Cl minus there. It is a chloride ligand, but you do not put the minus. You do not do that. It's taken care of in the overall charge here. Right? If you see here, the Cl is -1. There are 2 of them, so that's -2. Cobalt, if the overall charge is +1, this means that the cobalt must be +3, because +3 minus 2 is +1. Okay, now you could have the chloride ligands like that, or you could have the chloride ligands. What other way could you have the chloride ligands? You could have the chloride ligands next to each other, and then the water molecules like that, then fill it in. Square brackets plus. Okay, this is called the trans isomer because the chloride ligands are 180 degrees away from each other. Called the trans isomer. It's a stereoisomer. This is called the cis stereoisomer because the chloride ligands are 90 degrees away from each other. And these are stereoisomers of each other, the trans and the cis. Okay, now you also get this if you had this complex ion. Right, if you have this complex ion, so if we take platinum, okay, 2 ammonia ligands and 2 chloride ligands. Okay, now this complex ion has no overall charge because this is -1, which is -2. Platinum is +2, so it's got no overall charge. Now there are only 4 ligands. Okay, so this takes a shape with just 4 ligands. It's called a square planar shape. Okay, the bond angle is 90 degrees. 90 degrees bond angle. It's called square planar. Okay, now you could have the C chloride ligands next to each other, and the ammonia, because remember the lone pairs on the nitrogen, the ammonia ligands next to each other, and that would be called the cis isomer. Okay, if you had it the other way, just draw it again. Sorry, my drawing is not very good. Okay, if you had the chloride ligands opposite each other and the ammonia ligands opposite each other, okay, then that is called a trans isomer. And again, they are stereoisomers of each other. Same structural formula, but different spatial arrangements. Okay, so this is a really well-known one, the one I've drawn here, right? This is called, this one here, that one there, right, is called cisplatin. Cisplatin, and it's an anti-cancer drug. It's an anti-cancer drug, and it works by binding. It binds to the DNA in cancer cells, preventing division, preventing cell division, preventing division. And it's a really well-known one. Okay, so this is stereoisomers called cis-trans stereoisomers. Okay, so getting a bit more complicated now. You know, like with stereoisomers, let's go back to the other sheet. Stereoisomers, you have cis-trans, but in all organic chemistry, remember we call them EZ in organic chemistry, don't we? And then there's another type of stereoisomer called optical isomers. Okay, you get the same thing in inorganic chemistry too as well. All right, so far all the ligands we've talked about so far, ligands, remember that's a ligand that bonds to the central metal ion. They've all been monodimeral dentate ligands, which means that they form one coordinate bond with a central metal ion, okay? But you can also get bidentate ligands. Now there's two really common ones, right? So a bidentate ligand, if we do this one first, right, it's one molecule, right? But can you see it's got two lone pairs of electrons? So it can donate two lone pairs of electrons to the transition metal ion and form two coordinate bonds. Okay, this one here is called ethane 1,2-diamine, and it can bite round twice. Okay, it's shorthand. Sometimes you see it or a shorthand name. It's just called EN as its shorthand name. Okay, another well-known bidentate ligand is this one here, which is the lone pair, and so it bonds here, and it's called the ethane dioate ligand. They're the two most common bidentate ligands. Okay, so let's just see it in action then. So if you take, right, we're getting there. Right, if you take, it's quite long. If you take, for example, nickel, the shorthand would be EN3. It's a neutral ligand, so the charge overall charge is 2+. Okay, so that means it's octahedral. There are only 3 ligands, but it is octahedral because each ligand bites twice. So if you get the shape, octahedral, okay? So a nitrogen and a nitrogen. There's a nitrogen at the end of each one. Okay, now that's got CH2, CH2, like that, because it's wrapped around the ethane diamine, and then you need the H2 and H2. And you do that on each one. CH2, MH2, you do that on each one. Okay, CH2, CH2, H2, H2. Okay, and that is 6 coordinate bonds, 3 ligands, and that's that. Now, you can have an optical isomer. Okay, optical isomer, which is a non-superimposable mirror image. Okay, N, 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 N. All right, so I'm going to do a shorthand, right? So this is a mirror. We're going to do a mirror image. Okay, can you see that those two are bonded together? So I'm just going to go like this, like a shorthand. Those two are bonded together. Okay, those two bonded together. Those two bonded together, and that is a mirror image, non-superimposable mirror image, and they are optical isomers of each other. Now ideally you need to make these models, and in lessons you will make the models, and you'll actually see this. Okay, there's another type of ligand, and it's a hexadentate ligand. Okay, what does that mean? Hexadentate ligand. It bites 6 times. Okay, and it's called EDTA. It's got a 4- charge, and again in lessons you'll see that it wraps around the transition metal ion, bonding 6 times. But we'll look at that in lessons as well. Okay, moving on quickly, right? Reaction you need to know about. These are all called ligands. Right, just to say, these are optical isomers of each other. Optical isomers. Oh, terrible writing. I think it's the pen. Non-superimposable mirror images of each other. Okay, non-superimposable mirror images. I'm going to change the pen, see if it makes any difference. Right, so another thing you need to know about is ligand substitution. Okay, giving you a lot of information here, right? So ligand substitution. Oh, that's better. Ligand substitution, right? If you take, let's take for example, Oh, which example shall we take? Shall we take this one here? If you take copper and it's 6 water molecules, it's complex ion, okay? Those water molecules can be substituted. If you add concentrated HCl, remember this is blue, a blue solution. It's all solution, okay? If you add concentrated HCl, then ligand substitution happens. The water molecules gets substituted with the chloride, so it becomes CuCl4. Now the overall charge, because copper's 2 plus, that's 4 minus, the overall charge is now 2 minus aqueous plus 6 waters, because remember we swapped them, okay? This is called ligand substitution, and this colour is actually yellow colour, and it's in equilibrium. This is in equilibrium, right? And you can move it on either side, right? It's called ligand substitution. Now the funny thing here is this is octahedral, but this has only got 4 ligands, right? And this is not square planar, this is called tetrahedral. Remember your shape, your tetrahedral shape, bond angle 109.5 and 2 minus, okay? It's a tetrahedral shape. And this is because the chloride, remember tetrahedral is 109.5. The chloride ligand is larger than a water ligand or ammonia ligand, and it needs more room, so it forms a tetrahedral shape. Okay, and that's ligand substitution. Other common ones you need to know about, that's one. Other common ones you need to know about is the copper one. Oh, not copper, we've done copper. Cobalt, the other common one is cobalt, and it's really similar. Cobalt 2 plus. If you add concentrated HCl, remember cobalt is pink colour, and then it forms cobalt 4 ligands, 2 minus plus 6 water. It's in equilibrium. I should be doing an equilibrium error. That is a blue solution, okay? The other common one you need to know is if you take ammonia, all right? If you take ammonia, take the copper, take that, yeah, which is blue, and you add ammonia, and you add excess ammonia, you add a lot of ammonia, okay, that's blue solution, you get this, you get ligand substitution, 4 ammonias, 2 waters, still 2 plus charge, plus 4 waters here, and this is a deep blue, really lovely deep blue solution. But what you see first in this reaction, and you'll have a go at it in the lesson, first you'll see you get the blue solution, then you see a blue precipitate form, and the blue precipitate is copper hydroxide solid. You keep adding ammonia and you get the deep blue solution. Okay, anyway, that's called ligand substitution. The last, nearly come to the end, right? The last thing, let's just take, let's just ignore that for a second. Let's take this here. Okay, let's take that, right? That one there, okay? If it's in equilibrium, so if it's in equilibrium, what can we write for this reaction? Okay, because we can add water and move it in the direction we can move the equilibrium. If it's in equilibrium, we can write Kc. Let's write Kc for this, right? So if you write Kc for that, right? Got to be really careful with your square brackets. Actually, it might be easier. I'm doing it on a clean piece of paper. Clean piece of paper, that'll be easier. Alright, so I'm just going to write the same thing again, but just doing it on a clean piece of paper. Okay, cobalt plus 4Cl minus, CO, cobalt, Cl4, 2 minus plus 6 water. It's in equilibrium. I have to keep forgetting to write. All right, Kc equals concentration, now be careful, concentration of your complex ion times the concentration of water to the power 6 over the concentration of the reactants, or square brackets, concentration square brackets, concentration of chloride to the power 4. Okay, so that's Kc. Be really careful with your square brackets. Okay, so we're going to rearrange. We're going to bring the water, because that's times. Remember, it's all times. We're going to rearrange it and bring the water down here. Okay, but write everything else exactly the same. Everything else exactly the same. Concentration of the cobalt, water 6, 2 plus, concentration Cr minus 4, like that. Okay, now because we've got a lot of water, there's lots of water, this is all aqueous, right? All aqueous, there's lots of water. The concentration of the water is effectively constant. If you add a little bit more, it doesn't make any difference. So this is a constant divided by a constant. So we're going to call that K stab. Give it a new name, right? K stab is called the stability constant. And K stab equals all of that, okay? You've got to be really careful when working out your units, because this is to the power 4 there, so be very careful. What does K stab mean, right? If K stab is a large value, right, it's a large value, the position of equilibrium lies where? On the right. Yeah, just like Kc, if it's a large value, it lies on the right. Therefore, what does that tell you? Therefore, the complex ion that is formed is stable. Okay, easily formed, it's easily formed, is easily formed and stable. Okay, so the larger the value of K stab, this is more easily formed, it has strong bonds, it's more stable. Okay, and again, you need to be careful working out your units of K stab. Should we just have a quick go? Let's have a quick go because I've got a bit of paper left. K stab in this case would be concentration, the units, okay, would be concentration divided by concentration to the power 5. Concentration to the power 5. Okay? Because concentration to the power 5. Cross out one of the concentrations, take it to the top line, concentration to the power minus 4, bring the minus 4 into the brackets, mole minus 4, dm, this is times, dm 12. Ideally you should put the positive indices first.